topic today, which is basically on adder design, since we're doing our CAD 4. So we'll discuss that. Typically, this is the PowerPC by IBM, 604. It's about 20 years back. Now the different things like the instruction cache and data caches are much bigger sizes. But this is just to give you some sort of relative sense of the commercial processor, where you have the general purpose registers that you have done. You can see that this is a part. And we will talk about the execution unit, which is the part of the integer unit. But then it has also floating point and other features which you are not going to do that. Fetch and branch unit we'll talk about later when we talk about the program counter, instruction registers, and data registers. We will later on throw in some memories using some generators for instruction cache and data cache. There won't be any phase lock loop because your chip is small, so it doesn't require synchronization of clock at different places. And so what we'll do is that we'll talk about the arithmetic logic part corresponding to the integer functions. So an adder, all of you are familiar with, comprises of two data input, A and B, and a carry input, C, and it provides two output, sum and carry out. So if there are three different inputs are there, it's called a full adder, and the sum is basically the checkerboard pattern of the input A, B, C, which is A, B, or B, or C, and that's what you can see over here. And C out is the majority functions, majority of the A, B, and C. That means C out is AB or BC or CA, BC in and C in A. We can write this also AB plus C in A plus B. So this is the full ladder, and the sum S is A exclusive or B exclusive or C in. So now we can see that the carry out comprises of an AND function here and an OR function there. So we can think of the full adder comprises of half adder, and the half adder has also two outputs, AB S half adder and C out half adder or CO half adder. So sum is A exclusive or B, and this is AB. So this is what the half adder is. full adder is now the reason I'm doing this is these expressions you can implement in many ways. But when you design a larger adder circuitry, you'll find out that unless you are careful how you implement this function, you will not get good performance. So one thing is that in order to create full adders, or rather the adder chain, we will have to take advantage of the half adder. So that's why the functionality of the half adder, which is basically two data input and it generates a carry out, which is AB, and sum is A exclusive of B. Now the full adder, we can see that the majority function is whenever two of the inputs or more input, two or more inputs is 1, output is 1, otherwise output is 0. So there are 4 cases corresponding to B, C, 1, out, A and C1, out, C out is 1, A and B are 1, C out is 1, and all A, B, C in are 1, out, C out is 1. So let us pay attention to the carry out function, because this is pretty straightforward. This is a checkerboard pattern. It's called checkerboard because if you draw the Karnaugh map of, these are the data input and C in, this is the carry in, 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. So if you see the function sum, A exclusive or B exclusive or C in is 0 here, 1 here, 1 here, 0 here, 0 here, 1 here, 1 here, 0 here. So that's why it's called checkerboard pattern. What is the problem with the checkerboard pattern? You really cannot minimize the function. So either you use 1, 2, 3, 4, 3 input AND gate and an OR gate to implement the function, or you use the exclusive OR gates. Now the exclusive OR gates are not available just like that. So we need to still find out what we need to do to implement the sum function in a way. So that's the difference between logic design and the circuit design. Logic design, yeah, this is good, and you don't have to really bother. But you are a chip designer. If you just transcribe that logic function, then you'll find out that your performance will not be very good. So there are some things you need to do to improve the performance in terms of speed, and those are the things we'll talk about. But before that, let us pay attention to, so let's also draw the path for carry out, which is AB plus C in into A plus B. So whenever 2 or more inputs are 1, then the output is 1. So here output is 1, here output is 1, here it is 1, and here it is 1. The rest of the places is 0. So that's the Orthogonal map for the carry out. So what we are seeing here is that depending on the values of A and B, here A and B both are 0, 0, and carry out is 0. So we can say that carry gets killed whenever A and B both are 0, 0. Similarly, when both A and B are 1, 1, C out is 1. So irrespective of the value of the input carry, output carry is generated. So this is corresponding to generating. So we have two different situations depending on the values of A and B. Now, if A and B are differ, here it is A is not equal to B, A is not equal to B. If A is not equal to B, then what you see is that carry in over here, carry in 0 propagates as 0